In this video, I'm going to tell you how to find the area inside a parametrically defined curve. And to develop a formula, we need to go back to what we already know about finding the area underneath a curve that's defined as y equals a function of x, right? What we did was we took little tiny rectangles, right? Then if we looked at them a little more closely, we saw that they had a little bit of width, maybe about delta x's worth of width, and a height given by f of x. Okay? But in this video, I'm going to want to just call that y. That height is y, because y is equal to f of x, right? And this is the area between f and the x-axis. So it's the y-coordinate of f of x minus the y-coordinate of the x-axis, which is 0. Okay? And then we found that by adding up a whole bunch of these rectangles that really had height given by y and width given by delta x. And then as the number of rectangles went towards infinity and their respective widths went towards 0, the sum became an integral, and we were integrating y dx. Usually we said f of x dx, but I'm going to call this y dx for now, as x ran from x equals a to x equals b. Okay? And so what we're going to want to do now is say, okay, what if this was a parametrically defined curve? Okay? What if instead of y equals f of x, this was r of t is a vector valued function with, some x coordinate and some y coordinate that are each functions of time. That traces out a curve in the plane. Okay, now if you're in my multivariable calculus class, you should be pretty familiar with the situation. And what I'm going to say is that what's going to change about our rectangle is, well, really not a whole lot. It's still going to be this, except the height is going to be given by y of t, and this, that's not looking very good. I could do better than that. Height given by y of t, and width still given by delta x. Okay. So in the same way, we're going to be adding up a bunch of rectangles that have height given by y of t, and width given by delta x, and as we know what happens as the number of rectangles goes towards infinity and their widths go towards 0, this will become, okay, a y of t times dx between two x values. But y is a function of t, so we're going to need to kind of translate this integral into the t world. And so if I just say that the x coordinate over here is x equals x of t, and I take the derivative of both sides with respect to time, I'll get dx dt is equal to x prime of t. And then I could multiply both sides by dt and say that dx is equal to x prime of t dt. And so I'm a little closer, right? I'm going to say that this is going to become y of t times dx is x prime of t dt. Okay. But the bounds of integration are feeling troublesome because a and b are x coordinates. Okay. And so if I say that this is, x equals a happens at time 1, okay, what that really means is that x of t1 equals a. And if this is t2, and we're just saying that this is some t2 where x of t2 equals b. Okay. So if this integral I've got on the far right side is an integral in t, I'm going to need to integrate from t1 to t2, and I'll just have to be careful about what are these that get me the starting and ending places of my region that I'm trying to find the area of. So let's do a quick example. Right? This is the formula that we're going to use to find the area inside a parametric curve. And I guess by inside, I mean between the curve and the x-axis. So let's work a quick example, a familiar example, the area of a circle. Okay? This is going to be a circle. Let's just say it has radius a. Right? I'm not going to commit to any specific radius. Say we know that the area of a circle is pi times a squared in this case, where the radius is a. But we're going to need to parametrize this curve. So we need to write down an x of t and a y of t for it. So r of t, which is this curve, is going to be, well, we know how to parametrize a circle. It's going to be a times cosine t and a times sine t. And if you're not in my multivariable calculus class, so you're in my AP calculus class, what this is it's like the parametric equation situation where x of t equals a times cosine t and y of t is a times sine t. Okay. So if I want to find the entire area, what I'm going to do is I'm going to start with finding this area I'm shading in yellow and then doubling it. Okay. So the area I'm looking to find is equal to twice the integral from two different t values. We'll have to figure out what that means. But y of t, which is a times sine of t, times x prime of t dt. Okay. Well, if this is x of t, then I can say that x prime of t is going to be the derivative of cosine t with respect to t is negative sine t. You might be a little concerned about that negative. It's like, oh man, I don't know how I'm going to get rid of that negative over the course of this integration. But if we look at the actual balance of integration, if we were integrating this with respect to x, we would go from negative a to a, right? We would go from the left side of the circle to the right side as we were integrating forwards. Okay. So that means we know what this is on the unit circle. This is t equals pi. And this over here, this is t equals 0. And since if I was integrating this as y as a function of x, I would go from negative a to a. Now I'm going to be going from pi to 0. And that kind of backwards integration is going to take care of that negative in the negative a sine t. Okay, from here, we're going to say that this is all right. Maybe I'll reverse the bounds of integration and remove the negative. So and maybe factor out those two copies of a. So I'll get 2a squared times the integral from 0 to pi of sine squared t. Now, I'm going to need to, in order to run this integral by hand, I'm going to need to remind you of a trig identity. And that would be, pardon me, that cosine squared t equals, no, pardon me, it's a double angle formula. Start off with cosine of 2t equals cosine squared t minus sine squared t. Then we know that if I want to substitute on sine squared t, I need to get rid of this cosine squared t. So what I'm going to do is I'm going to substitute on that. Cosine squared t is 1 minus sine squared t. And if I were to combine all this, I would have 1 minus 2 sine squared t. And if I solve for sine squared t, I'd have cosine 2t. Oh, wait, no, hold on. 1 minus cosine 2t all divided by. And maybe instead of writing it as a fraction like that, I would actually do the division and say that's 1/2 minus 1/2 cosine 2t. And I can find an antiderivative for these things. So I'll have 2a squared multiplied by antiderivative for 1/2 is going to be 1/2 t. And an antiderivative for negative half cosine 2t is going to be negative quarter. I'm going to have to divide by that 2 for the chain rule of sine of 2t. I'm going to check that mentally for a second. 1/4 cosine 2t multiplied by 2. Yeah, okay, I'm satisfied with that antiderivative. All right, I'm going to evaluate that from 0 to pi. And I'll get 2a squared. Okay, half of pi minus 1/4 of the sine of 2 pi. Well, the sine of 2 pi is 0. And then when I plug in x equals, or t equals 0, I'll get half of 0 minus 1/4 of the sine of 0. And, okay, I've got 2a squared times pi over 2 is pi times a squared, which is what we already knew, right? The area of a circle. So that's how it works. If we want to find the area inside a parametric curve, we might only be finding, part of it, but we can use that formula that I'll scroll back to here right now. That formula that's highlighted in gray, we can use that to find the area inside the parametric curve. And that's all I got for you in this video. Thanks for watching.